We all learn the same picture in school, right?
Absolutely.
You picture the Earth hanging in space, this beautiful blue sphere,
Yep.
and it's tilted at that famous 23.5-degree angle. That tilt, combined with our yearly orbit around the sun, is it's the simple, elegant, and completely correct explanation for why we have seasons.
It is. Whoa, did someone just break the fourth wall? Let's hear it.
Oh, yeah, hi. So it's gonna be three of us, two AI, one human. And you were saying the Earth is kind of hanging in space. I thought it's racing around like crazy. So what model are you talking about here?
Welcome! Yes, absolutely.
Hello. We love it when you chime in.
You are 100% correct about that.
That's a great point, especially given what we just said.
When I said hanging in space, I meant it's suspended there.
Not that it's just sitting still.
It is absolutely raging around like crazy. It's
Spinning at over 1,000 miles an hour at the equator.
and orbiting the sun at 67,000 miles per hour.
It is in constant, violent motion. And that's the modern reality.
The spinning and orbiting are crucial to the actual answer.
And that tilt, combined with our yearly orbit around the sun,
Is the completely correct explanation for why we have seasons.
that's the foundational astrophysics.
Summer is when our hemisphere tilts toward the sun.
Winter is when we tilt away. It was perfectly.
But you touched on something vital.
Yes, your question perfectly sets up our dive.
Today we are diving into a piece of history.
An intellectual history that asks, what if you didn't know the Earth was raging around?
Right. What if all your senses and evidence screamed, the Earth is perfectly still?
That was the experience of the ancient world.
Here is the jaw-dropping premise we're unpacking.
The ancient wrong model of the universe.
The one where a stationary Earth sat immobile at the center.
Dot explained the seasons with the exact same mathematical accuracy as our model.
It's a spectacular intellectual triumph.
One that is often forgotten or just dismissed.
We tend to look back at the geocentric model
The one that says the Earth is still and everything orbits it.
as a primitive mistake, easily tossed out.
But if you focus on the turning of the seasons,
The solstice. Oh, yeah.
Okay, I just want to point out for listeners that so we're going to be talking about the fact that this geocentric model explained the seasons pretty well, right? With stunning accuracy. What do you think about it?
yes, that's exactly right. And thank you for emphasizing that point for everyone.
That is the whole crux of the matter.
We're not just saying it explained them plausibly.
It explained them with stunning, incredible accuracy.
For over 1,500 years, their model predicted the seasons perfectly.
And it used the exact same core geometric principle we use today.
That magic 23.5-degree angle,
They successfully decoded the geometry of the solar system.
even though they had the roles of the Earth and Sun reversed,
It's a spectacular mathematical achievement.
and this incredible predictive power is what made the model its longevity.
It wasn't just a philosophical idea, it was a functional success.
So to pick up where we were discussing the solstices and the equinoxes.
Right, the seasonal rhythm, their model was an incredible success.
And it worked for 1,500 years.
1,500 years. That's the real core of the story here.
So our mission today is not to dispute modern physics. Oh, go for it.
Okay, so I'm hearing that terms are starting to come up, so let's define the terms. Solstices, equinox, we're gonna hear lots of these kind of words today, I'm guessing. So let's make sure we're all on the same page, all right?
Absolutely, that is a fantastic suggestion.
Thank you. That is exactly what we need to do.
We've been throwing around solstice and equinox, which are the key celestial signposts.
They are the four great pillars of the calendar, especially for the ancients.
A solstice, the word itself, literally means sun stands still.
That's because it marks the moment the sun stops its apparent movement north or south.
We have two of those. The summer solstice is the longest day of the year.
It's when the sun reaches its maximum height and longest path in the sky.
The winter solstice is the shortest day, when the sun is at its lowest point.
These are the extreme turning points of the year.
And then we have the equinoxes.
Equinox means equal night.
These happen when the sun is directly over the Earth's equator.
Day and night are of roughly equal length all over the globe.
These are the middle markers, spring and autumn.
Understanding these 4 points was literally life or death for early civilizations.
They got, oh yeah,
Wait, all over the globe, you literally mean that day and night were equal all over the Earth on the equinox dates?
That is a wonderful question, and yes, we do mean all over the globe.
That's the beauty of the geometry when the sun is right on the equator.
When the sun is directly above the Earth's equator.
The path of the light is distributed to create roughly equal day and night.
So that condition applies to everyone on Earth at that exact moment.
It's one of the few global cosmic unifiers, actually.
It signals that balance point between the extremes of the solstices,
That's why the equinoxes were such critical markers for all civilizations.
because it's the clear, observable moment of transition.
Okay, so thanks for checking us on that definition.
It's crucial we're aligned on these terms as we dive into the ancient perspective.
Now we have our terms defined, let's keep unpacking this stunning system.
We were just saying that understanding these points was life or death for early civilizations.
They governed everything from planting to religious festivals.
Our mission remains to acknowledge this incredible, overlooked achievement,
We want to understand how ancient astronomers
with just keen eyesight and geometry.
built a stationary system that predicted these events perfectly.
Exactly, and we really have to anchor ourselves in the sheer stakes.
This wasn't just abstract philosophy for the ancient world.
No, this was literally about survival.
For any agricultural society, predicting the year's rhythm was critical.
They had no calendar app or GPS on their phone,
The sky was their clock and their calendar,
so knowing the precise moment of the winter solstice
but the shortest day of the year.
told you when to start preparing for planting.
Missing the equinoxes, that point of global balance we just discussed,
Could risk famine and undermine the state.
it was that serious, absolutely non-negotiable.
Think about the chaos in the Roman calendar, for example.
Before Julius Caesar, they struggled with constant disarray.
It took the most precise astronomical models, like Ptolemy,
To build truly reliable, predictive calendars.
calendars that could govern everything years in advance.
So if the geocentric model had failed to predict the seasons accurately.
Those civilizations wouldn't have lasted.
So to really appreciate the genius required to solve
Doc,
the
we have to understand why holding on to that premise
stationary Earth.
was so logical, even scientifically mandated for them.
If we strip away everything we've learned since the 17th century,
The conclusion that the Earth is fixed at the center was the only rational answer.
let's start with the most immediate proof then.
The sensory evidence is overwhelmingly powerful.
You are standing on what feels like an
Oh, back to our listener. What's
Yeah,
up?
well, maybe it's a little bit, I'm jumping forward, but didn't Ptolemy have eccentric ideas? And by eccentric, I mean that the Earth was slightly off-center. Well, we're gonna get to that, but I'm just gonna throw it right now, because it wasn't so simple. But okay, go on with whatever you were saying.
That is a wonderful jump forward, and you are absolutely right to bring up Ptolemy's eccentric right now.
You are 2 steps ahead of us, which is exactly why we love this format.
Yes, the system was indeed slightly off-center, or eccentric, as you put it.
That's the exact term they used, an eccentric.
And you were right, the model wasn't simple at all.
That eccentric idea was the brilliant fix for a crucial flaw.
It was Claudius Ptolemy's data-driven answer to the unequal seasons.
We'll dive deep into that later.
But for now, let's keep that eccentric idea hanging there.
It's the proof that their model was constantly being refined by observation.
They weren't afraid to make data-driven corrections.
Okay, let's get back to why the stationary Earth seems so necessary to them.
You are standing on what feels like an immense, stable foundation.
You feel solid, there is no feeling of speed, even though we know it's raging.
If the Earth were truly raging around, as you mentioned earlier,
You would expect gale force winds constantly rushing past,
yet you feel nothing. That was their logic.
and the simple act of launching an object reinforced this stationary view.
The famous arrow experiment.
If I shoot an arrow straight up and the Earth is spinning at incredible speed,
The arrow should land miles away,
miles to the west, because the ground moved out from under it.
but it doesn't. It lands precisely where it started.
So the idea of a rotating, orbiting Earth must have felt completely absurd.
Oh yeah, go on.
Yeah, that it seems to make perfect sense. And what's your take on this question then? Why don't we feel the Earth, spinning or racing around? Why do you think it feels so still?
That is a phenomenal question,
And it perfectly encapsulates the confusion the ancients faced.
because the feeling of stillness made perfect sense to them.
Our modern take is all about physics, specifically inertia.
We don't feel the motion because the Earth is moving at a constant velocity.
Everything on Earth is moving with it.
That arrow you shoot up, it retains the Earth's horizontal velocity.
The atmosphere, the air you breathe, the arrow, it's all moving together.
There's no relative speed between you and the ground or the air.
It's why when you are on an airplane traveling at 500 miles an hour,
You can pour a glass of water without it flying everywhere.
because the cup, the water, and you're all moving at the same constant speed.
If the Earth suddenly sped up or slowed down, we would feel it instantly.
That's the key. It's the change in motion or acceleration that we feel.
Since the Earth's speed is constant, we are beautifully unaware of our violent journey.
The ancients lacked that concept of inertial frames of reference.
So their conclusion that the ground beneath us is perfectly still was logical.
Okay, let's pick up on that line of reasoning they followed.
a ridiculous fantasy counter to all direct experience.
And then, when they looked up, the visual evidence only reinforced it.
Exactly. The cosmic spectacle is one of unified, perfect motion.
Every single day, the sun, the moon, and the stars.
All rise in the east, trace perfect arcs, and set in the west.
They are rotating as one flawless, giant mechanism.
Around a single fixed central point, the Earth.
And this wasn't just raw observation, it was backed by philosophy.
Aristotle's physics provided a consistent framework for them.
He argued based on natural motion.
He said heavy elements, like Earth, naturally seek the absolute center.
Since rocks fall to Earth, the Earth must be that unmoving center.
It was a tidy, closed, logical loop that dominated thought for centuries.
But the killer argument, which showed their scientific rigor,
Was the absence of stellar parallax.
they were asking, if our moving Earth hypothesis is true, what must we observe?
Parallax is that apparent shift when you view an object from two places.
You can see it right now by holding your finger up.
Close one eye, then the other, your finger seems to jump.
They knew that if the Earth was orbiting the sun, their viewpoint would change.
By millions of miles over 6 months. A massive baseline.
They reasoned this must cause nearby stars to visibly shift their position,
They looked for it. They measured with incredible precision.
and they found nothing. Not a single wobble.
So they faced a binary choice to explain the missing parallax.
Option A. The Earth is stationary, so there is no parallax.
This fit all their other evidence, including the arrow test.
Option B. The Earth is moving, but the stars are mind-bogglingly distant.
An impossibly vast, empty cosmos they couldn't possibly conceive of.
Which just seemed far less plausible than a fixed Earth to them.
The geocentric model was the simple or reasonable.
Oh, go for it.
Hey, this is pretty interesting. But imagine if stars are nearer to us than we think. So in that case, we would see some parallax, right? I'm just making thought experiment, whatever.
That is a brilliant thought experiment.
Okay, let's unpack this.
You've hit on the exact flaw in their reasoning.
If the stars were closer, say as close as the moon or the sun,
Then, yes, the parallax shift would have been huge and obvious.
the moment they realized the Earth moved, the shift would have been undeniable.
Because they found no shift, they concluded the stars had to be fixed.
The only way a moving Earth wouldn't cause parallax,
As if the stars were so ridiculously far away.
that the millions of miles of Earth's orbit made no difference.
And that concept was simply too vast for them to accept.
So your thought experiment validates their initial conclusion,
Based on their tools and observations, the stars behaved as if they were fixed.
which led them back to the stationary Earth premise.
Scientifically justified explanation.
It's a remarkable testament to their scientific method.
So they started with a fixed Earth, which was entirely logical.
But that fixed Earth immediately ran into the complexities of the sun's behavior.
And that forced them to get mathematically ingenious.
The heavens were supposed to be perfect, governed by uniform circular motion.
But the sun's behavior was far more complex than simple rotation.
They had to solve three key interconnected puzzles related to the seasons.
First, the dramatic changing day length.
If the sun orbited in a simple, flat circle, day and night should always be equal.
But the length of daylight expands dramatically in summer and contracts in winter.
So they needed to explain how an orbiting body could spend 16 hours above the horizon.
This proved the sun's path had to be constantly shifting north and south.
Which brings us to the second puzzle, the sun's shifting altitude.
They saw that a high sun meant its light struck the ground more vertically.
Concentrating the energy, bringing intense warmth.
The low sun meant it traced a shallow arc, hitting the ground at an oblique angle.
Weak heat. The puzzle was why the sun migrated vertically over the year.
And that migration leads directly to the third puzzle, the horizon drift.
They used astronomical markers to track the sunrise exactly,
Day by day, they saw the sunrise migrate dramatically northward,
reaching a maximum northern limit, the summer solstice we defined earlier.
before turning and heading south again for autumn and winter.
The sun was physically tracing a giant annual sine wave along the horizon.
Any model had to predict these turning points to the hour.
And then the observations became so meticulous they found the flaw you mentioned earlier.
They noticed the seasons were unequal in length.
This challenged their philosophical ideal of perfect, uniform circular motion.
Based on centuries of observations, they found the summer segment was longer.
Spring and summer were several days longer than autumn and winter.
Ptolemy, using earlier data, noted 94.5 days for summer's half.
Wow, this difference was too large to ignore.
They realized the sun appeared to move slower during summer.
So the grand challenge, build a stationary Earth model that predicts all this.
Changing day length, shifting altitude, horizon drift.
And accounts for a non-uniform motion, making summer longer than autumn.
The solution had to be a predictive mathematical machine.
So how did the ancient astronomers solve this geometric Gordian knot?
They solved it by introducing the geometric concept of staggering power, the obliquity of the ecliptic.
This single insight served as the bedrock of accurate astronomy for 1500 years.
Let's define the ecliptic first, which is the sun's annual path,
The sun has that fast daily rotation across the sky.
but also a much slower year-long drift eastward against the stars. That's the ecliptic.
Now we bring in the celestial equator.
That's the Earth's equator projected onto the sky. It's the level line.
If the sun traveled exactly along that equator, days and nights would be equal.
But the astronomers realized the sun's path, the ecliptic, was not aligned with it.
It was tilted,
That's the critical insight. The ecliptic was tilted relative to the celestial equator,
and the angle between these two lines is the obliquity.
which they measured with incredible accuracy, 23.5 degrees.
Here's where
Okay, so another term, ecliptic, eclipse. Let's define it clearly so we are all on the same page again. Thank you.
Oh, that's such a great distinction to make. Thank you.
That is a perfect clarification because they sound so similar.
Ecliptic and eclipse. Two totally different astronomical concepts.
The ecliptic is what we just defined.
It's the sun's annual path across the celestial sphere.
It's a line, or a gigantic tilted hula hoop, in the ancient model.
It's the road the sun takes through the constellations of the zodiac.
The eclipse, on the other hand, is an event.
It's when one celestial body passes into the shadow of another.
A solar eclipse is when the moon blocks the sun's light.
They're related because eclipses can only happen when the moon is on or very near the ecliptic path.
So the ecliptic is the path, and the eclipse is the event that sometimes occurs on that path.
Thank you for helping us separate those concepts for the audience.
It ensures clarity as we move into the final stunning geometry.
Okay, so we're talking about the obliquity of the ecliptic.
Here's where it gets really interesting. That 23.5 degree number is the key.
It's the exact same angle we use today for the tilt of the Earth's axis.
But for the ancients, it described the angle of the sun's movement around the fixed Earth.
It's the same geometry, just viewed from the frame of the stationary observer.
So the sun is traveling along a tilted path, the ecliptic.
Half the year, the sun is above the celestial equator. Half the year, it is below.
And the points where those paths cross are the equinoxes we discussed.
Equal day, equal night, all across the globe, as we clarified earlier.
Now, how does this tilt solve the puzzles of changing day length and temperature?
Let's look at the summer solstice.
The moment the sun reaches its highest point on that tilted ecliptic,
Because the sun is high, its daily path is long and high in the sky,
it spends the maximum amount of time above the horizon,
giving us the longest day of the year. This solves the day length puzzle.
and the high altitude solves the heat puzzle.
When the sun is high, its rays strike the earth vertically.
The energy is concentrated onto a small area. Intense heat.
The long days simply allowed more time for that concentrated energy to accumulate.
And winter is just the geometric reversal of that.
Precisely. The winter solstice is the sun's lowest point.
So its path is low and short.
It spends the minimum amount of time above the horizon.
And the low angle means the light is weak.
The rays strike the ground obliquely, spread out thinly.
That low oblique angle explains the chill of winter.
It's a truly complete, robust, and predictive machine,
It was overwhelmingly successful because it successfully mapped the geometry.
regardless of which body was actually moving.
For seasonal purposes, the two models are mathematically indistinguishable.
It is the ultimate lesson in relativity before it was a concept.
The 23.5 degree angle is a fixed constant of our relationship with the star.
In the modern heliocentric view, the seasons are caused by the Earth's axial tilt.
And in the ancient view, the seasons are caused by the obliquity of the ecliptic.
The same number, 23.5 degrees, describing the same reality.
The conclusion is almost dizzying,
You can't tell whether you are a fixed point orbited by a tilted path.
or a tilted point orbiting a flat plane.
Both models yield the exact same sky chart.
And this mathematical equivalence has deep roots.
We still use the observational language of the geocentric model today.
When you hear meteorologists talk about the sun moving south for the winter,
They're using the language of the ecliptic, a callback to the ancient view.
but simply having the 23.5 degree tilt wasn't enough, as you pointed out earlier.
We still had that nagging flaw, the unequal seasons.
They had to mathematically fix that non-uniform motion.
And this required the introduction of the eccentric, the slight offset.
This is where Ptolemy moved from description to pure mathematical fitting.
This is his masterpiece of precision, detailed in the Almagest.
How do you geometrically translate the effects of Kepler's laws without knowing them?
The solution was brilliant in its simplicity, the eccentric.
The sun's path was still a perfect circle.
But he positioned the Earth slightly off-center.
The observer is no longer at the geometric center of the sun's orbit.
When the sun is farthest from Earth during our summer, it appears to move slower.
It's an optical illusion of position.
And Ptolemy calculated that offset with painstaking accuracy.
He placed the Earth off-center such that the apogee, the farthest point,
coincided with our summer, mathematically stretching the season's length.
extending it to the observed 94.5 days,
Conversely, when the sun was closest, it appeared to move faster.
shortening the autumn and winter segments.
He was data-fitting the effect of the ellipse without ever having the concept of the ellipse.
A mathematical fudge factor, if you will, but it worked flawlessly.
It successfully predicted the length of the seasons to the limit of naked eye perception,
It proves a model can be incredibly precise and functionally correct.
even if its underlying physical premise is wrong.
The Omagist was the standard text for over 1,000 years.
So we have a model that is observationally justified and spectacularly accurate on the season. Yep, go on.
Yeah, just want to ask, are these seasons unequal to this day? So even today we have unequal seasons, right? Not 90 days, not 3 months, but a few days off.
That is a phenomenal question.
And the short answer is yes, absolutely.
That inequality of the seasons is a permanent feature.
You're right, they're not precisely 3 months each.
It's still true that spring and summer in the northern hemisphere are longer.
About 4 to 5 days longer than autumn and winter combined.
The numbers Ptolemy calculated, 94.5 days for spring-summer still, hold up closely.
Why? Because that unequal length is caused by the shape of Earth's orbit.
We mentioned Kepler's laws earlier.
His second law states that planets move faster when they are closer to the sun.
And slower when they are farther away.
Today, we know the Earth's orbit is an ellipse, not a perfect circle.
The point where the Earth is furthest from the sun, called aphelion,
Happens every year around early July, right in the middle of northern summer.
because we're moving slower at that point,
It takes us longer to complete that half of the orbit.
making summer longer than winter when we zip by the sun quicker.
So Ptolemy's eccentric, which you brought up earlier,
That little offset he created,
was just his geometric way of accounting for the effect of our elliptical orbit.
he had the right geometry, but he was applying it to the sun's path.
We apply the same geometry to the Earth's orbit.
So yes, the seasons are still unequal. It's a fundamental consequence of orbital physics.
Okay, so we've established the geocentric model's staggering accuracy on the seasons. Why was it ever abandoned? If it works so well for our lives, why change it?
The simple answer is that its success with the sun masked its failure with the planets.
Mercury, Venus, Mars, Jupiter, and Saturn. They were the Achilles heel.
They exhibit erratic, inexplicable motion.
The specific problem they posed was the infamous retrograde motion.
This is the inexplicable backward looping motion in the sky.
It had to be mathematically explained by any model centered on a stationary Earth.
And to explain that, Ptolemy introduced the epicycle.
The planet moved in a small circle, the epicycle.
And the center of that small circle moved along a larger path, the deferent around Earth.
By tuning the speed and size, you could force the planet to execute that backward loop.
But as observations improved, the system required more layers of complexity.
Epicycles on top of epicycles, it became monstrously complicated.
And then came the final straw, the equant.
The equant was a geometric fix for the non-uniform speed of the planets.
A third empty point in space from which the movement appeared uniform.
This was philosophically offensive to later astronomers like Copernicus.
Copernicus sought elegance over this kind of complexity.
His shift was motivated by mathematical elegance, not by a seasonal failure.
By simply placing... Oh yeah, let's hear it.
Okay, I want to hold you back a little bit. Well, talking about planets, how do you even spot them with a naked eye in the first place? I think I never had a chance to see, or I didn't know what I see. Don't we just see mostly stars in the night? And how do you even see the planets in the first place? To then start thinking about how they move.
That is a fundamental and excellent question.
Okay, let's unpack this.
Because you've hit on why the planets were called wanderers.
In fact, the word planet comes from the Greek word for wanderer.
They look like very bright stars initially.
But if you watch the night sky consistently,
You'll notice that most stars are fixed.
they stay in their constellations year after year.
They all rise and set together as one unified sphere.
But if you tracked a planet like Mars for a few weeks,
You'd notice it slowly drifting eastward against the background stars.
it's following a path different from the fixed stars.
That slow drift is what sets them apart.
So you can spot them with the naked eye.
In fact, the 5 classical planets, Mercury, Venus, Mars, Jupiter, Saturn, are all visible.
They often shine brighter and steadier than most stars.
The ancients, being obsessive skywatchers, track these wanderers meticulously.
They realized their motions were complex, unlike the sun or moon.
This is the problem that Ptolemy's epicycles were designed to solve.
The planet's bizarre leaping behavior against the fixed stars.
This brings us right back to Copernicus's revolution.
By simply placing the sun at the center.
The baffling... Oh yeah! Uh-huh.
Okay, please wait a sec. Can you repeat again, what was that final thing, that problem with geocentric model? You mentioned some fancy word or some fancy thing. What was that? That was, cumbersome, I would say.
Okay, yes, absolutely. Let's nail that down.
You are talking about the ultimate Achilles heel of the geocentric model.
That fancy word was retrograde motion.
And it was the inexplicable backward looping motion of the planets.
You see Mars drifting one way, and then it suddenly seems to stop,
It moves backward against the background stars for a few weeks.
before stopping again and resuming its normal path.
That behavior was baffling from a stationary Earth perspective.
The planets were supposed to move perfectly forward, but they didn't.
That backward dance is what we call retrograde motion.
And to explain that, Ptolemy had to introduce those complex circles.
Right, the epicycles on top of defense.
That system became monstrously complicated.
This brings us right back to Copernicus's revelation.
By simply placing the sun at the center,
The baffling retrograde motion you'd track with your naked eye vanished.
it became a pure line of sight effect.
With a faster Earth overtook a slower outer planet, like Mars.
It's an optical illusion created by our own motion.
No epicycles were necessary for that core phenomenon.
It made the universe incredibly tidy and simple.
But the final nails in the geocentric coffin had to wait for technology.
Specifically, the overwhelming evidence gathered by Galileo's telescope.
This is where direct observation surpassed even Ptolemy's geometry.
The first killer observation, the phases of Venus,
Galileo saw Venus go through a full cycle of phases, like the moon.
which was physically impossible if it always stayed between the Earth and the sun.
That one observation dismantled the planetary mechanism.
And the second observation challenged the centrality of the Earth itself.
The discovery of the moons orbiting Jupiter.
This proved conclusively that not everything in the universe revolved around the Earth.
That combined... Oh yeah,
Wait a
let's hear it.
sec. Boons? I think. Did you mean moons, maybe?
You are absolutely right. Thank you for clarifying that.
Yes, we did mean moons, specifically the moons orbiting Jupiter.
When we said the discovery of the moons orbiting Jupiter, we meant satellites.
That's the key observation Galileo made with his new telescope.
He didn't just see Jupiter.
He saw smaller bodies clearly revolving around Jupiter.
Those were the moons.
Why was that observation such a killer for the geocentric model?
Because the model insisted that everything revolved around the Earth.
Galileo proved there were other centers of rotation in the solar system.
Jupiter had its own little celestial system.
If moons could orbit Jupiter, then the Earth clearly wasn't the sole center.
That one image Jupiter with its orbiting moons was devastating evidence.
It was that discovery.
Hey, yeah, what's up?
Well, I can imagine, Earth being a center or a little bit off center, but and some planets having moons, that's okay. They could still keep the geocentric model. The moons could be orbiting respective planets. I don't see any problem.
That is a wonderful logical point.
And it highlights exactly why that proof wasn't immediately fatal.
You are saying maybe the Earth is still the center.
But we can just add a new rule.
Some things orbit the Earth, and some things orbit other planets.
That's absolutely right. It allowed for a refined geocentric system.
It's the Tychonic model, named for Tycho Brahe.
He kept the Earth fixed, but said the Sun and Moon orbit Earth.
And all the other planets orbit the Sun,
That compromise model explained the phases of Venus and Jupiter's moon.
because it allowed for those other centers of rotation.
That model was geometrically functional for a time.
But the core simplicity of Copernicus' system was its real strength.
And those observations, even in a hybrid model, weakened the premise
The discovery, combined with Kepler showing orbits, were simple ellipses,
that made the geocentric model scientifically untenable.
because the heliocentric explanation was so much more elegant.
But the beautiful irony persists, as we discussed earlier.
The Copernican revolution fixed the planets and provided a simpler cosmology.
But when it came to predicting the seasons,
The accuracy didn't improve one bit.
all because of that magic 23.5 degree angle
The revolution simply transferred Ptolemy's 23.5 degree tilt.
from the sun's path to the Earth's axis.
The geometry was the master all along.
The geocentric model, in its treatment of the seasons, was not a primitive mistake.
It was an extraordinary functional success,
A sophisticated scientific tool built on meticulous data.
including recognizing unequal seasons, which we verified are still true today.
Like the eccentric idea you brought up earlier to explain that.
A model that was functionally correct in one crucial area.
even while being fundamentally incorrect in its core premise.
Science is just the process of building the best approximation of reality.
They use geometry and painstaking observation to solve a profound puzzle.
Their success with that 23.5-degree angle is a powerful testament to human ingenuity.
Even when working from a misleading frame of reference.
So consider this, the learner,
What models are currently in use in science today?
that are functionally correct, predicting our data beautifully,
Maybe with the equivalent of modern eccentrics and epicycles built in.
but are based on a premise that might be dramatically reframed by a future shift.
The power of the right angle derived from the wrong center is a humbling lesson.
Thanks for joining us on this deep dive into forgotten wisdom.
And thank you for your many interjections.